Excellent. So, as a brief recap, we're going to be talking in this class about radiation as emission and reception of thermal energy from surfaces. The surfaces can be exposed to vacuum or exposed to a transparent medium such as air. Things like water, we have discussed, are opaque to thermal radiation. And why we say that some things that look light are opaque or is because thermal radiation heat exchange depends very much on the wavelength. And although in the visible range, things might look clear, at the longer wavelengths that correspond to lower temperatures, things might be opaque to that radiation. That's the case of water. We said that when we talk about radiation, not only we talk about the wavelength of this radiation, but also a directional distribution. And we talk about these three concepts of reflection, absorption, and transmission. And in such a way that some surfaces absorb some amount of thermal energy, those would be semi-transparent, and some surfaces absorb 100% of the energy. Those would be, no of the energy is transmitted, those would be the opaque surface, whether it's all absorbed or all reflected, right? That we call them opaque. We talked about a few concepts about the emitted power, that is the power that is emitted because of the temperature of a body. We talked about irradiation, that is the amount of thermal energy that comes by radiation in. Then radiosity, that accounts for all we emit plus all we reflect. And then we introduced the concept of black body. And black body at each wavelength a black body is a body that can emit the maximum amount of radiation at a given wavelength. So all the other real life bodies will emit somewhat less radiation, never more. In addition, a black body is a diffuse emitter. And why we discuss black bodies is because this is an awesome proxy for many real life surfaces that in reality are not 100% a black body, but are like 90% a black body. And we can start making some sort of calculations that are relatively easy with those. When a body is not a black body, some calculations we're going to see later today become very difficult. So this is a good model. And what do we learn from black bodies? We learn that the hotter they are, the more radiation they emit, something we already knew. But in addition, that the hotter they are, the shorter the wavelength they emit. And that's something we also knew, because when something starts getting hot, we say it's red hot, then yellow hot, then white hot. And white hot in reality is because it's not only emitting in the red and in the yellow, it's emitting the green and the blue, all those wavelengths that we perceive through our vision as white. And humans have evolved such that our eyes are tuned to the radiation that comes from the sun. And one of the first interesting facts we discussed last class was that our eyes are tuned to these frequencies, wavelengths between 0.4 and 0.7 microns that corresponds to the wavelength of the sun, that corresponds to 5,800 Kelvin, which happens to be the temperature of the surface of the sun, 5,800 Kelvin. And we also saw how when we talk about photography or when we talk about light bulbs, we tend to assign a number with a K as if it was a temperature. In reality, a fluorescent light bulb is not at 3,500 Kelvin, much less at 5,500 Kelvin, but they emit light that has a peak at that wavelength. as if it was that temperature, right? In reality, they are not, but they are trying to use a language similar to the one of an incandescent light bulb that is indeed at 2700 Kelvin, very hot. That's why they have a tungsten filament, so it doesn't melt out. And for that reason, because it's 2700 Kelvin is so much lower than the 5800 Kelvin of the sun, we see these lights of a light bulb as reddish, right? It's quite interesting. We talked about how real, from the point of view of directional emissivity, when the normal emission is what is typically tabulated here near zero, but as we have shallower and shallower angles, a non-conductor such as wood starts emitting less and less, such that if I look at the radiation emitted by a non-conductor that can be wood or brick or plastic at a shallow angle, I see it as emitting less radiation. But in metals, it's exactly the opposite. When we're at a shallow angle, we see quite a bit of radiation come out. And I was showing you this that comes not from my lab, but is a type of research in which we are involved, in which we see this droplet of molten metal that has these lighter edges that are not reflections of anything, and they do not mean higher temperatures, but mean higher emission, just because as we have shallower angles, we have more radiation, and the thermal camera is fooled into believing it's hotter, but it's not. And so a few interesting things. So we talked about spectral emissivity and how things like plastics have a higher emissivity and metals have lower. And for that reason, for example, in this kettle, that is an experiment I did with elementary school kids, the lid seems to be super hot, same as the lid seems to be hot, but in reality, it wasn't that hot. It's just that it's plastic and has a high emissivity. And the body of the kettle seemed to be a little bit colder, but in reality, was not necessarily colder. It's that it's a shiny metal and emits less radiation. So the thermal camera is fooled into thinking that less radiation is coming out. So then we start to talk about things like transmissivity. And we talked about this interesting fact for which the concept of wavelength is essential, is how things such as glass, they're nearly perfectly transparent, right? 95% transmissive in the visible range. That's why we see, a glass window, it's awesome. But at longer wavelengths that correspond to lower temperatures, such as thermal radiation at temperatures of everyday life, is opaque. And that's why we see glass as opaque in a thermal camera, why in our problems we have assume water and glass was always opaque. And also, an example I mentioned, how this meant a revolution in industrial lasers, because lasers of CO2 that used to be common and they're moving into obsolescence run at 10 microns. You could not use transparent optics. Was a huge problem. You had to work with mirrors. But now modern lasers run at about just a little bit higher than 1 micron, and you can use transparent optics, like fiber optics, all type of normal photographic optics. And it's an amazing thing, and it's changing life. This is the last slide we saw on Monday, in which we talked a little bit about global warming, and we saw something interesting. We saw this red curve is the spectrum of the sun, and how much of this light actually comes into the earth. This we see here, these little dips, are because either water vapor, typically water vapor, is absorbing some of this light, but a little bit of it. And this is at very short wavelengths because the light is coming from the sun at 5800 Kelvin, right? And these are the properties of water vapor with light of this wavelength. Now, this light of the sun comes to Earth, warms it up. The Earth for sure is not at 5800 Kelvin. The Earth is more or less at 300 Kelvin, give or take. And that radiation now at lower temperatures because of Wien's law is at much longer wavelengths. Now, this radiation in the Earth has to go somewhere, right? And here's the catch. Outer space is at 0 Kelvin and the Earth is more or less at 300. So this wants to go to outer space. But guess what? At these wavelengths, water vapor in the atmosphere has a lot of absorption, right? Look at this. This is the absorption of water vapor. And you saw here before how these little mountains would absorb some amount of the light of the sun coming in. Not a big deal. But you see these huge mountains here? Now, these huge mountains here say that the radiation from the Earth that wants to go back to space at 0 Kelvin does not make it. Does not make it because it's absorbed by the water vapor. And that's why we see here that this blue mountain is small. This mountain should attract either of these three curves here, but it doesn't because the water vapor kills the radiation here and traps it into the Earth and absorbs this other radiation at even lower wavelength, trapping it into the Earth, right? This is what is called the greenhouse effect. Light can come in through the glass because the glass is transparent to the light of the sun, but the thermal energy that is absorbed cannot be radiated out because it's absorbed by the glass, that now the glass is transparent for the light of the sun, but it's black for the radiation from the plants inside the greenhouse. Now, this is water vapor. People tend to talk about CO2, and this is a story. Although water vapor tends to catch most of it, it doesn't catch all of it. And so there is an amount in this thermal balance that is related to carbon dioxide. If we move the amount of CO2, or if we move the amount of methane that is even smaller, what is happening is the thermal balance is altered. Now, if I tell you the Earth is more or less 300 degrees, you know, because you have read the news, that if instead of 300 is 301, lots of cities are going to be flooded, right? And 1 in 300 is a very small part. And this is what is causing this difference. This is under our control. This is not. This is part of the balance of the Earth. But this is something we are making. Here, methane is something that the cows are making from what I read. Super interesting. If you go back to the second, what was that? If you go back, I think it's to the second or third week of class, you'll see I put a supplemental material, a proper analysis of thermal balancing the Earth. Analysis with the tools we have in this class. It's not a super fancy supercomputer analysis in which they account for how much gets absorbed in the atmosphere and how much gets radiated out. It's super interesting. And right there you can see what's going on. Very interesting. I want to show you a really cool video that somebody made at a university, but they didn't put what university it is. So I don't know who to credit for. But it's so amazing that these people really deserve to be well credited. So I'm gonna play it for you here, the last 2 minutes. And left is a thermal camera. Right is a normal camera. Check it out. Plexiglass. Is it transparent or is it not? Isn't that interesting? So it depends. If you're at the wavelength of visible light, it's transparent. If you're at the wavelength of infrared, that is what the camera on the left is transmitting, is capturing, is quite opaque. So now the guy is playing. So he's touching the plexiglass. When his hand lets go, the plexiglass is warmer, and the handprints we see are just the radiation, the thermal radiation from the warmer parts of the plexiglass. What he's doing just playing is a technique that is used in for non-destructive testing of carbon fiber parts in airplanes. Because if you warm up all the surface, then it's eventually going to cool down, but the parts that are delaminated, they don't. You see, thermal radiation reflects quite a bit too. He has this, probably looks like an aluminum plate. So you can still make mirrors for thermal radiation. I don't know what he's doing there. Gotta love his friend on the phone in the background, huh? This part blows my mind. Check it out. This is a trash bag, but the trash bag is magic. Did you know that trash bags were transparent to thermal radiation? I didn't. So this is kind of the opposite of, is the opposite of a normal glass. Look, a black garbage bag. The question that comes into my mind is, shouldn't we make the lenses for CO2 lasers out of garbage bags? I'm half joking, but the other half is serious. Isn't that incredible? Anyway, that's he starts to play with water, but that is another story. I think that video is amazing. The guys who did it was really onto something, and it helps us see that heat transfer, when it comes to radiation, is a very different animal that is by conduction or convection, especially because of this business of the wavelength, such that glass, plexiglass, or normal glass becomes opaque to radiation but transparent to visible. And garbage bags, I think they're polyethylene, they are transparent to infrared and opaque to visible. Who knew? Amazing. Here I have a schematic, and of this schematic, this is a good part of the book that has a derivation that is kind of, it's in words and it's a little bit hard to follow, but this is the bottom line. We have said that that reflectivity plus absorptivity plus transmissivity is 1, right? And so how much this alpha is the absorptivity. Then we also talked about how when something is hot, it emits. So you can emit or you can absorb. It's 2 different things. What Kirchhoff's law says, and has a little bit of a derivation in the book, is that in the end, the emissivity and the absorptivity are the same under common conditions. It's not always the same, and I'm a little bit puzzled exactly about when is which, but emissivity and absorptivity are the same typically, and in this class, we're gonna say always. So epsilon emissivity, alpha absorptivity are gonna be the same for us. And on that note, I want to switch to the quantitative part of the class. That is the one that relates to our assignment 2 due on Monday. So let's talk about radiation exchange between surfaces. And so the first important concept is that of solid angle. This schematic here on the left is a normal angle on a plane. So the normal angle on the plane, you can define as this, this segment of an arc divided the length, right? And that would give you the angle. This divided by this other one. This is for a plane angle. in radiation, things go out in space, not on a plane, such that we need to define a solid angle. And a solid angle sometimes is a difficult concept to grasp, but I'll do my best. So instead of being this arc divided the distance, this is going to be a spherical cap divided the distance squared, such that if I go all the way around and divide by this radius, in this case, it's going to be 2 pi, right? 2 pi r gives me this length. In the case of a solid angle, if I do this over all around, that would be the surface of a sphere, I would have that the total solid angle of a sphere is 4 pi. 4 pi times r squared gives me the surface of the sphere. So we're not going to be using this a lot, but you must be aware of this concept of solid angle, because when we do intuitive considerations, we'll be using these thoughts, if not the math. So if we have a radiating area, this dA1, we are radiating, if we put the right set of coordinates, we can define the direction of radiation with 2 coordinates, right? And it would radiate around a solid angle. So I'm skipping a few pages of the book, but now that we talked about a solid angle, we can talk about the view factor. Radiation is not a 1D problem, it's not a 2D problem, it's not a 3D problem, it's a 4D problem. And if we were talking about radiation in gases, a volumetric, that would be a 6D problem. We're not even talking about that. The easy one, that is the one we will talk about, is a 4D problem. 4D. And why is it 4D? Because it's 2D of a surface that matches the 2D of the other surface. We have 2 dimensions here, exchanging radiation with any of the other point in the other 2 dimensions of the other surface. So now we have to account for this solid angle that is coming out of here and how it is connecting to the other surface according to an angle, right? And if we were to do the math, which we will not, but if we were to do the math, we would see that this exchange of radiation would be related, it would be inversely proportional to the distance, the square of the distance. That's kind of obvious. And, but also involves the cosines of the direction in which the radiation is emitted. We're not doing the math formally, but you can see intuitively why, right? Like it's not the same emitting directly out that directly at a shallow angle, in which the way we would view the surface is kind of shallower. And that's what the cosines account for. If we do the integral over all this surface, so let's pick one point. This point views all this other surface J. So we have to do a 2D integral over surface J for one point. But here we have a 2D surface. So we have to do an integral here over an area of something that was already an integral over the other area. If we were to do that, we would be defining this view factor. And here's the really cool thing. I have like butchered decades of mathematics of lots of talented people. And after like waving my hands around what a view factor is, I tell you how the view factor relates to how two surfaces see each other. And then we define this view factor Fij that accounts for these cosines, that accounts for all the integral, right? Accounts for the distance between the surfaces, right? This view factor is our ticket to salvation. With these view factors, we can solve really complex problems. You know why? Because some poor soul spent 4 years of a PhD doing this integral. And that poor soul is not you, unless you want to go to grad school. Every time we're gonna be using a view factor, we're 4 years younger than the person who had to suffer that until they got it. So this is a formula to calculate a view factor that if you don't have it, by now you can put it in MATLAB or Mathematica or a bunch of modern tools we have with which we could calculate this view factor. We see something cool here already. With this definition of the view factor, if I multiply, I pass this AI up here, I would have AI times Fij equals this integral. And you see that in this integral, I have theta I and theta j and AI and AJ. I could flip I and J and nothing would happen. So we get, without doing any math, just from looking at the shape of this integral, an important factor, important property of this view factor, that is that AI times Fij would be the same as AJ times Fji. This is amazing. Doesn't look like amazing, but it's amazing because it helps us do some tricks with which we can make inferences without doing the integral, inferences that are not tabulated without ever touching an integral. And that's what we want. If we ever need to do an integral, means we're pioneering something, and that something is quite complex. Typically, we seldom need to do integrals. We should have them in our back pocket, but seldom use them. There are other properties of these view factors. And I'm talking about the view factors, you don't know exactly what to do with this concept other than the concept embodies the integral. I'll tell you these properties, and then we're gonna do a problem. Number one property, and to start training ourselves into the intuition of view factors, is that the view factors, say this surface I, right, against all this surface is the same as the view factor of this surface I against AJ plus AK or IN, right? What this says, and you can, I'm not doing the math, but you can see where it comes from, because essentially what this view factor says is I'm grabbing an integral and splitting the integral into smaller integrals. That's all we're doing. But from the practical point of view, it's amazing. Don't do an integral. Just says the view factor of this area against everything that is a bunch of other things is the same as the sum of view factors if I were to split this area. We will use this. Number two, the enclosure rule. The properties of the definition of view factor is such that if a surface is completely enclosed, then the view factor is 1. So let's see, this is surface AI, and it's completely surrounded by surface AJ. AI sees AJ, but doesn't see, for example, this other side. I want to be clear. For example, we made AI. This surface, I'm talking about this side of the surface. In this body, you would have a flip side. I'm not caring about that flip side right now. If I want to, that's another story. But I'm talking about this one surface. So this one sees AJ, but this surface here, AI, does not see anything on the other side, right? You can, this is like standing on the earth. You can look up to the horizon, but you don't look, you do not see below the horizon, right? This is, so to have an intuition for view factors, sometimes it's cool to imagine you are standing here and you're really small. You stand on this surface. What do you see? That is a really good thought experiment to deal with view factors. So if you're standing here, what do you see? Well, you would see this and nothing on the other side. In that case, when you're completely enclosed, this surface, the view factor is 1. Number 3, virtual surface. Let's say you have a crazy complex surface. I made here my interpretation of a crazy complex surface. What is the view factor of AI against crazy complex surface? If we were to do the integral, right? But this can be proved just by doing the integral and then seeing how things cancel. This crazy complex surface is exactly the same, mathematically exactly the same as if we had put a plain flat surface or any other surface that has the same view from this point. So if I were to stand here, I would see all this the same way I would see a flat surface, right? Much like if you go to the theater, they might make a fake scenery, right, in which they have fake perspective. This is the same, a real perspective, and this is the fake perspective. And it looks the same view factor. So this surface that I made with dashed line, let's call it a virtual surface, right? That's why I put V. Self-view. Let's talk about a surface that is convex, like a mountain. So each point on this convex surface has a self-view factor of 0. Because if you're standing here, you would be seeing that way and that way, but you don't see anything else. This surface does not see itself. Conversely, if we're inside a bowl, right, something concave, if you're standing here, you would see the bowl on the other side of you. So now the view factor is different than 0. Whatever it is, but it's different than 0. And then finally, this reciprocity rule that I mentioned before. These 5 rules, you don't need to memorize them, especially that there is no exam to memorize. But as you do the problem 2 in the assignment, the question A is about find some view factors. And by using these properties and some things that are tabulated in the book, you can calculate the things that are not tabulated in the book. And it's quite awesome. So these are the view factors that are tabulated in the book. In addition to these, and you do not need them for the assignment, but in addition to these, I uploaded 2 additional lists of view factors in a supplemental material. So if you ever in your professional life find yourself dealing with radiation, I put you everything, I put there everything I have. And I gave you everything I have for view factors for other conditions. So there are 2 approaches to this. One is they have these kind of formulas, right? And they say the view factor of surface I to surface J, right? And you see there like a half open book. What would this view factor be, right? And they put it here. View factor between 2 cylinders. This is really cool, right? We could consider in this case something like a heat exchanger exchanging heat by radiation. I mean, with this knowledge you have from radiation, but from this course in general, you can invent things that have never existed, and you can design them and ballpark them before you build them. That's the power we have. There are others like view factor between 2 parallel surfaces or 2 parallel disks, or rectangular surface with a common edge. Here we have the formulas, and here we have some graphs. My suggestion to you is that you always start with a graph, because with the graph, you can never get a crazy wrong result. If you want to have a sharp result, then you use the formula. But the graphs will take you pretty close to home most of the time. So you see the 2 parallel rectangles, the 2 parallel circles, and the 2 rectangles joined at 90 degrees and joined by the edge. These 3 are the same as these 3. You can use the formula if you wish, or you can use the graph if you wish. How does it work? Let's talk about black body radiation exchange. I will not talk in this class about gray body radiation exchange. Why? Because in black body radiation exchange, nothing gets reflected and we're happy people. When radiation comes to a body and part of it gets reflected, then it goes back and comes back and goes back, and there are ways around it, and there are formulas, the book explains it. I just feel that would be too much for all we're learning in this class. We have our hands full with the core just by learning about black body radiation exchange. So let's see. Let's talk about surface I exchanging heat with surface J. The amount of heat exchange is QI arrow J, right? QI to J. How do I calculate that? So it's going to be the area of surface I times Ji. This is the radiosity, right? So we're starting in the general terms. Radiosity is sending out all the heat by the thermal heat plus the reflected heat. This is the right way of writing it. Very soon we're going to see that really this is just black body emission, but not right now. And then multiply by the view factor, right? This is where view factors that I was talking to you in a very general terms, how view factors end up being a number that we plug into the equation. When we have done so far or problems that involve radiation, we were saying that radiation was exchanged to everything around, and all the surroundings, the T-SIR that we use, were completely encompassing. So because they were completely enclosed, the bodies we were talking about, the view factor was 1. And wink, wink, not, like we didn't need to worry about anything else. Now we're talking about things that are not completely enclosed. So we need to worry about this view factor. So because we're talking about black body radiation exchange, this radiosity, this amount of heat emitted, is just going to be the heat emitted by a black body. And here I'm using the notation of the book. So this is black body emission from surface I. So if instead of J, we have the black body emission, we have the same equation as before. Q from I to J is area of I, view factor, and black body emission. Now, surface J sends energy to surface I because it has a temperature other than 0 Kelvin. So I write the exact same equation, but I'm flipping I and J, right? So Qj to I would be area J, view factor from J to I, black body emission from surface J. Now, Qij is what I sends to J minus what J sends to I. Right? Now it's a net heat radiation heat flux, net radiation heat flux. So, and these equation numbers here, of course, are the equations where you can see in the book. So Qij, Qi to J here, we have it. AI, Fij, black body emission of I, Qji, the J to I, is here. And here the awesome thing happens. Because of these properties of the integrals, in which we are not doing the deep math, but we keep in mind the properties. And this property was trivial because was self-evident in the shape of the integral that we could flip I and J. We have AI, Fij, and here we have Aj, Fji, which happen to be the same. Also, we know that the black body emission was sigma Ti to the 4 for surface I, sigma Tj to the 4 for surface J. Very easy. So Q I to J, IJ, right? The net heat flux between I and J, and in this case, positive means emitting heat, and negative means receiving heat as net, has this expression here. Check it out. AI, surface area of surface A, surface I, sigma T to the 4 of I minus T to the 4 of J. This is almost exactly what we had before. Before we used to have an emissivity. And when you're completely surrounded, this emissivity didn't really matter. And we put it there, was not a problem. Now, because we don't want to deal with reflections that will give us headaches, we don't have an emissivity anymore. Emissivity would be 1 because it's black body radiation exchange. But we are bringing something new that we had not done when we had second week and we looked at heat transfer mechanisms. We have this Fij. We have this view factor that allows us now to exchange heat to many surfaces at different temperatures, in which we see a different surface in different parts, and they have different temperatures. So Qi, and again, now we would have a sign convention using these formulas. That means net heat out against a whole bunch of surfaces that would end up enclosing surface I is just the sum of the area I times the view factor of Ij, right? And the temperature differences to the 4th. This is awesome. Now we can do something we were not able to do in the whole term. Using this is what you're being asked to do in assignment 2. How does it work? I'm going to walk over a problem that is in the book, so you can go to the book and check it out. It says you have a cavity, and this cavity has 4 surfaces. These are kind of rings. 1 ring, 2 rings here, 3rd ring here, and then a bottom disk. 4 surfaces. All these 4 surfaces are at the same temperature. But what is outside is the surrounding, and the temperature is 1650 degrees C. Let me tell you, this is white hot. This would be white hot. And outside is 27 degrees, right? This is like a furnace cavity, the way they put it. And they ask a number of questions. What is electrical power? We would need to put a heater on top, in the middle, in the bottom. How do we go about this? This problem could not have been solved with what we knew before. We need this concept of view factor to solve this problem. So what we're going to do is start by defining some virtual surfaces. For example, here, they don't tell us what is outside. It just says the surroundings are at 27 C. The surroundings might have crazy shape, but we don't care because we have this trick of replacing a crazy surface with a virtual surface here on top. And we are going to call this like surface 5, right? But this is a virtual surface. There is nothing here. But from the point of view of view factors, this is all the surroundings, however crazy they are, they become a virtual surface here at the temperature of the surroundings, these 300 K. So these notes, in addition that you have it in the book, I have uploaded these notes into the supplemental material in radiation. So let's do 1. Heat exchange between 1. First of all, if all these surfaces are at the same temperature, there is no heat exchange between them because they are at the same temperature. I don't need to worry. But the real losses, for example, for surface 1, is whatever it goes out to the surroundings. And now we need to account for the view factor between this surface, surface 1, and the surroundings. And for that, I know that this is a circle is a disk, and the surface is another disk. We can go to the table and use the formulas in this case, or we can look at the graphs. And then we can calculate a power, right? A radiative heat flux using the formulas in which we have area times view factor times Stefan Boltzmann constant, T to the fourth of the disk minus T to the fourth on the surface. The interesting one is, let's use surface 2 as an example. Surface 2 does not lose heat to surface 1, does not lose heat to surface 3 or 4. So it's kind of tricky because it loses heat like as annular surface to the outside. There is no tabulation for that. However, we can make a virtual surface and do use tabulation. So what we're going to do is to say that instead of the exchange between surface 2 and 5, right? Let's talk about the heat exchange between surface 5, right? And this other surface here. This is a virtual surface between the rank 2 and 3. And I know this, that the view factor from 5 to this surface is the same as the view factor between 5 and surface 2 and 1, right? Because of this property that this virtual surface is the same as these other ones they see. View factor problems become some sort of a brain teaser in which we have to see how we transform what we have that might look complex into the tabulated forms that are quite easy, right? So in this case, we could we could say F5-2, right? From 5 to 2, that is the one that we really cared about, is between 5 and virtual surface and 5 and 1. And this is exchange between two disks for this one here and between two disks for this other one here. So we reduce the problem of going from this one surface, this one disk, to a ring, to go from one disk to two other disks, which we knew. And it gets solved quite simply then. Because it's 1:50, I'm going to stop here. I will have office hours. I will send the clarification about the assignment. And I would like to ask you if you, that you please fill up the class evaluations. I really care a lot hearing from you. I really want to make this class as good as possible. This has been super challenging, but I think it's been getting better as I've been learning and as we all learn to work in this online form. I really hope you enjoy the class and you have learned. I'll be super happy to discuss further when you have your final project. So if you want to do research projects next semesters like DRA. Thank you very much. Let's stop here. I have a question about the average for the last quiz. Today, I'm going to upload an answer key together with the statistics. I was hoping to do it before class, but it's going to happen after the office hours. Thank you, everybody.